In this video, we're going to discuss the magnetic force on a charged particle moving through a magnetic field. So from the demo video that we had earlier, we found that only charges that are moving will experience a magnetic force. So our equation should somehow take into account the fact that only moving charges will experience a magnetic force. And the form of the magnetic force is this. So this is the magnetic force on a charged particle is equal to the charge of the particle that is moving through some magnetic field, the velocity of that charge. This is a cross product, not a normal multiplication symbol. So it is the cross product of the velocity of the charge with the magnetic field. Notice that if the particle isn't moving, the velocity is 0 and the entire force is 0. For the moment, we are simply going to assume that a magnetic field exists. So at the moment, I will always provide you with some external magnetic field, and we will try to find the force due to that external magnetic field. We are not going to worry about how magnetic fields are generated yet. Okay, so just a few thoughts about this. First, it looks like we have a nice cross product here, and therefore we should be able to use the right-hand rule in order to find the direction of the force. So remember that our right-hand rule is that our index finger points in the direction of the first vector in the cross product, our other fingers point in the direction of the second vector in the cross product, and our thumb points in the direction of the resulting vector. So I've listed that here. Index finger points in the direction of V, our first vector. The other fingers point in the direction of B, our second vector in the cross product. And then our thumb points in the direction of the force. So let's just try to use this equation here in a simple example. So the example that we have is, imagine that we have a proton moving into the board through a magnetic field pointing upwards in the positive y direction. Now, we have set up a coordinate system to go along with this, and we should always check that our coordinate system is right-handed. That is to say that x cross y equals z. This is how right-handed coordinate systems work. If you don't have a right-handed coordinate system, your cross product will not actually work properly. So we better do that. Okay, so we want x cross y to equal z. We can simply right-hand rule it. X cross y equals z. Our resultant vector of x cross y does in fact point out of the board, and this is a right-handed coordinate system. So we can do the cross product using the right-hand rule in this coordinate system and find the correct answers. Okay, so our setup is that we have a proton, so it has a charge of plus E, where E is our 1.6 times 10 to the negative 19th coulombs. It has a velocity negative VZ z hat, so it has some velocity into the board in the negative z hat direction. And it is moving through a magnetic field that is only in the y direction, which we will write as by y hat. So by could be 5 millitesla, right? It's just standing in for some number that we can fill in later, right? Our goal should be to simply find the equation for this force on the particle and the direction of that force. We'll begin by simply using the right-hand rule, and then we will find this force using the actual mathematical form of the cross product. Okay, so let's begin with the right-hand rule. So our index finger is going to point in the direction of the velocity into the board. Our other fingers should point in the direction of the magnetic field upwards, and our resulting force should point to the right. So just based on the right-hand rule, I would expect that the force on this particle should be to the right. It's really good practice for you to do this along with the video so that you get used to quickly doing the right-hand rule, and it will allow you to double check your answers quite quickly. Okay, so now that we have a guess based on the right-hand rule, let's double check this using the math. So our equation is F equals QV cross B. So what we're going to do is we are going to make our determinant matrix here. So we're going to make x hat, y hat, and z hat the first row. The second row gets filled in with the components of our velocity vector, but velocity is only in the z hat direction. So we have 0, 0, negative z hat, or sorry, negative vz, not z hat, negative vz. And our magnetic field has only a y component, so we fill in 0, by, and 0 for our third row, and then we take the determinant of this matrix. And again, the way that we do that is we have x hat multiplied by the determinant of this submatrix. So we take x hat and we multiply it by the determinant of this matrix here, which is 0 times 0, which is 0, minus Vz times By. Vz times By, well, that's all it is. Next, we move on to our y hat component. Our y hat component, we cross out the top row and the middle row, and we take the determinant of this matrix here, or these components together. And remember that the y hat component comes with a minus sign out front. So we have y hat multiplied by 0 times 0 minus negative Vz times 0, which is all 0. So there is no y component to our force. And then we can do the same thing with our z hat component. Our z hat component is going to be multiplied by the determinant of this submatrix, which is 0 times by minus 0 times 0, which is, of course, all 0. So in the end, we get our charge multiplied by the only non-zero component of our cross product, which is Vz times By. Because we had two minus signs here, it turns out that our total force is in the positive x hat direction, as we would expect. So we end up with a force of E times Vz times By in the positive x hat direction, where again, in another example, we could assign a specific value to this velocity and magnetic field, so we could turn this into a number. Now let's look at what happens if we have exactly the same situation where a charge is moving into the board in the minus z direction with a uniform magnetic field pointing in the y direction. But now, instead of a positively charged proton, we have a negatively charged electron. Now, the first thing that I want to do with this is I actually want to look at the mathematical analysis of this situation and see what happens there, and then see what we can learn about using the right-hand rule for negative charges. So what we have done is we have written F equals QV cross B. Now, instead of a positive E for a charge with the proton, we have negative E for an electron. Our determinant has stayed exactly the same. Notice that our velocity and magnetic field did not change here, so nothing about our matrix is changed. When we take the determinant of this matrix, which is equivalent to doing the cross product, we find exactly the same result in our brackets here, and we find the same result here. However, we have this negative charge out front bringing a minus sign along with it, which means that our total force has exactly the same magnitude as it did before, E times Vz times By, but now instead of being in the positive x hat direction, it is in the negative x hat direction. So what has happened is, instead of feeling a force to the right, as we found with the proton, we are now feeling a force to the left. Now, what we can do with our right-hand rule is we can use exactly the same right-hand rule. That is, velocity is into the board, magnetic field is up, force is to the right. And what we do is we just flip our final result. So whatever final result we get from our right-hand rule, if our charge is negative, we flip the result 180 degrees, which is the same as multiplying by -1 in our cross product here, right? So the rule for using the right-hand rule on magnetic fields here is if you have a negative charge, you flip the direction of your final force. We can also write this as negative charges feel a force in the opposite direction of positive charges due to a magnetic field. So if a positive charge would feel a force to the right, our negative charge will feel a force to the left. Now let's look at another example of using this magnetic force equation on a particle moving through a magnetic field. So now we have changed from, instead of a particle moving into the board, we now have a particle moving up and to the right through exactly the same magnetic field. So our magnetic field still points straight up, and it's still given by some magnitude multiplied by the y hat unit vector. Okay, so our velocity can be written as Vx in the x hat direction and Vy in the y hat direction. And just to be a little more clear, we're actually going to break this down into the component that is parallel to the magnetic field and the component that is perpendicular to the magnetic field. The y component here, so Vy, is the component of my velocity parallel to the magnetic field. And the x component, Vx, is the component of my velocity perpendicular to the magnetic field. And if we remember our discussion about cross products, we remember that cross products pick out components of two vectors that are perpendicular to one another. So we expect that only the perpendicular component of our velocity will contribute to our magnetic force here. So let's take our velocity vector, which we've written just generically as Vx x hat plus Vy y hat. Again, we could plug in specific values for these Vx and Vys, but we want both Vx and Vy to be positive here because our vector is pointing up and to the right. Okay, so now let's look at our determinant equation. So our force is equal to the QV cross B. We have a positive charge here, which means that we have a plus E. We say we have a proton, for example, would have a charge of positive E. And we need to take the determinant of this matrix here. So when we look at our x component, we're looking at this submatrix for our x hat, and both of our cross terms are multiplied by 0, so there is no x hat component to our force. Likewise, when we look at y, we are going to be cross multiplying the corners of this lower section, and there are no non-zero terms there. The only thing that is left is the z component, which will be Vx multiplied by By minus Vy times 0, leaving us only with Vx times By in the z hat direction. Okay, so we now get a magnetic force that is pointing out of the board, and notice that the only term in our velocity that is left after we take the cross product is the part that was perpendicular to the magnetic field. Only the perpendicular velocity, our x velocity, contributes to our magnetic force. Our y component of velocity got multiplied by 0 each time, such that it did not contribute to our cross product. So the last thing that I want to talk about with this example is, can we use the right-hand rule here even though our two vectors are not perpendicular to one another? And the answer is definitely yes. So the way that we do a right-hand rule for two vectors that are not perfectly perpendicular is we simply still point our index finger in the direction of the first vector, our velocity, right? Because our first vector is velocity here. The index finger points in the direction of the first vector. Our other fingers point in the direction of the second vector, which is up. Notice that I'm not making a 90-degree angle here. I'm allowing the two vectors to point in the direction that they actually point. But my thumb still points straight out of the board. So I end up with velocity, magnetic field. My thumb points straight out of the board, These two components, the two inputs, my index finger and my other fingers, my two inputs, do not need to be perpendicular. They can be any two vectors. The output, my thumb, does have to be perpendicular. So it always has to point at a 90-degree angle to both of the input vectors, which is out of the board in the positive z-hat direction, just like I found from my mathematical calculation. So we could have gotten the direction only. We can't get the magnitude from our right-hand rule, but we could have gotten the direction only simply by using the right-hand rule with the velocity, magnetic field, and force. Now let's quickly recap what we have learned about this magnetic force just by analyzing the cross product in that example. So first, we found that the magnetic force is always perpendicular to the direction of the particle's velocity and perpendicular to the magnetic field. Remember, this is what cross products do. They give us a resulting vector which is perpendicular to both of the vectors of the cross product. So our force is always perpendicular to the direction of velocity and perpendicular to the magnetic field. Another thing that we found is that only the component of the velocity that is perpendicular to the magnetic field actually contributes to the total force. Any component of the velocity parallel to the magnetic field does not contribute to our cross product and therefore does not contribute to our total force. Finally, we found that we can find the direction of the force on an object using our right-hand rule, where the index finger points in the direction of the velocity, our other fingers point in the direction of the magnetic field, and the thumb points in the direction of the force. Now let's just note that there are three separate situations in which a particle will experience no magnetic force while being in a magnetic field. One is that the particle is at rest. Obviously, if I set velocity equal to 0, there will be no force. Additionally, if the particle moves along the direction of the magnetic field or against the direction of a magnetic field, it will feel no force. This comes from our idea that only the components of the velocity perpendicular to the magnetic field contribute to the magnetic force. If I am moving along the direction of a magnetic field line, then there is no perpendicular component of my velocity. My entire velocity is parallel to the magnetic field, and the cross product of two parallel vectors will always be 0. Therefore, there will be no magnetic force if a particle is moving along the direction of a magnetic field line. Finally, if the particle is neutral, we know that the force depends on charge. If Q is 0, there will be no magnetic force. Finally, we learned that the negative charges feel a force in the opposite direction that positive charges do when experiencing the magnetic force. We found that this came from the addition of a minus sign in front of our force equation when we solved. So our final direction gets reversed when we have a negative charge. This is exactly similar to the case where the force on an electron in an electric field is exactly the opposite of the direction of the force on a proton in that same field. Just like in electric fields, we had to flip our direction to deal with negative charges, or the direction of the force on negative charges. We have to flip the direction of the magnetic force as well to deal with negative charges. This means that if we use the right-hand rule to find the direction of our force, we need to flip our final result of the right-hand rule in order to get the correct force direction for negative charges. Luckily, if we do it mathematically, the minus sign from the charge automatically flips the direction for us, and this equation will always give us the proper direction for our magnetic force as long as we do our cross product correctly and include the negative sign on the charge.